And again, I apologize to my two students who are doing Physics 12 without having done Physics 11, because I'm going to be explaining some concepts that I spent hours and hours elaborating in Physics 11. We're going to jump right into it. We're going to be looking at one-dimensional force problems where everything is still in a nice straight line, where nothing is at an angle. Did I say angle? Nothing is at an angle yet. And some classic one-dimensional force problems include the elevator or apparent weight problem, air resistance, friction. We'll do a whole lesson on friction. And then the many-body problem, where there's more than one mass, where we modified our equations so that instead of winner minus loser equals ma, it became winner minus loser equals m all a, where we got to cross out tension. The Atwood machine, you might recall, where one mass went up and one mass went down and all that stuff. Last year, I introduced the concept of what we called the normal force. What's the normal force? It's the force that a surface exerts to prevent an object from sinking into it. If all of you lift your feet up right now, lift your feet up off the ground right now, can you feel the chair pushing up on your body? The chair is exerting a normal force because gravity is trying to accelerate you down, but because you're not accelerating, I know there must be an identical force up the same size as gravity. It's the force with which the floor pushes on you. It's the force that's keeping your binder from sinking through the table. And it's also the value that a bathroom scale reads when you stand on it. Scales don't read mass. Scales don't read weight. Scales read the normal force. There will be questions when I ask you to tell me what a bathroom scale is reading. In your free body diagram, you're not going to put F scale, you're going to put normal force, and that's what you're going to solve. And I think we proved that. I have a bathroom scale right here. I had somebody stand on it and do deep knee bends, and we noticed the scale kept moving, but their mass wasn't changing, and gravity wasn't changing. So we thought about it for a while, and we realized what was changing on the scale was the normal force, because that's what a scale measures. By the way, if I jumped out of an airplane, when I jumped out of an airplane, if I had stood on the scale while I was in free fall, what would it have read? 0. Why? No normal force, no ground pushing up on me. Was gravity still acting on me? Yeah. So my weight is mg, is the force of gravity. The normal force is sometimes called your apparent weight. It's the weight that you think you feel, because what you think of, AJ, as your weight is actually how hard the ground is pushing up on you. That's why if you're piggybacking someone, you feel heavier. Your mass hasn't changed. What's changed is how hard the ground is having to push up to keep you from sinking into it, because now it's having to counteract somebody else's mg and your mg, but your mass hasn't changed. I'm being really nitpicky here, but it's an important distinction. Your weight is mg, Braden, your apparent weight is the normal force. I showed you a video last year of a kid experiencing on a roller coaster his first changing normal force, right? I can see some of you are a little unclear, so we'll look at it again. Put your pencils down, look up. Right now, all of you feel a normal force that equals gravity, and all an amusement park ride does is it messes around with the normal force. We can't change gravity, but we can change how hard the ground pushes up on us. Here is a young kid on his first roller coaster ride. He's about to experience his first changing normal force, and your job is to see if you can spot exactly when the normal force, how hard the ground is pushing up on him, changes. Nice high roller coaster. Good height. I think the normal force changed right there. What this child is feeling is a smaller than normal. And that's unusual for us. All of us have experienced a bigger than normal force. All of us have experienced the ground pushing up on us harder. When you piggyback someone, for example, and almost everybody when they're a kid has given somebody else a piggyback, or if you're on a swing set, at the bottom of the swing is pushing up on you harder than mg. There's a bigger than normal. Come on in. So all of us have experienced a bigger than normal, but there's not very many childhood experiences where you experience a smaller than normal force. The only two I can think of is when you're on a trampoline while you're in the air, but then the normal force is 0, and that you have experienced every time you jump off of a playground apparatus, or every time you jump off of a small wall, and that you do as little kids as well. Jumping off of a high dive, you have a temporary normal force of 0, but even that a lot of kids won't do because some kids don't like that no normal force feeling. I can't think of a consistent childhood activity where you feel the ground pushing up on you less. And if someone thinks of a good one, let me know. I'll add it to my teaching. Now, this child is in fear. I could never stop this video here. This child is about to make one of the best emotional recoveries I have ever seen. Because right now, he's pretty scared. He's pretty scared. Oh, see, he just started to have fun. He just realized this is fun. He's smiling, and even better yet, oh, he even gets his hands up. I am so proud of him. Look at that recovery. So, an amusement park ride can change the normal force. Make it lighter, for example, when you're going down that big first hill of the roller coaster. Heavier at the bottom, and there's other amusement park rides that make the normal force heavier as well. There is no equation for the normal force. There, on your formula sheet, there's nothing that says Fn equals and some formula. You can only figure it out from your free body diagram. A person, example 1, a person with mass little m and weight big W is in an elevator standing on a bathroom scale, and let's pretend that it's a physics scale that reads newtons instead of kilograms. Displays newtons instead of kilograms. If the elevator starts at rest and accelerates up, what will the scale read? W? More than W? Or less than W? Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So if you were standing on a scale in an elevator that was accelerating up, would the scale read your weight, more than your weight, or less than your weight? Who says it would read your weight exactly the same weight as before? Got one? Who says more than your weight? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Who says less than your weight? 1, 2. Convince me. What might this be a good job for? What? So if I was answering this question, I would draw a free body diagram. I'm going to do it right here. What are the forces acting on this person? Get the obvious one. Which way? Okay. I'm going to put a W there because they wanted me to use weight for mg instead of mg, but if you put an mg there, I'd be fine with that. What else? Which way is this person accelerating? Which way must there be an unbalanced bigger force pointing? So I know there has to be an arrow pointing that way. What force is that? Well, it's the floor pushing up on your feet. But what name have we given to the force that's the floor pushing up on your feet? Who's winning? As an equation, we would have this. Normal force minus, normally I write mg, but this question wants me to use weight, okay, equals ma. Now, this is asking about the scale reading. No, it's not, because what does a scale actually measure? So let's get the Fn by itself, because that's really what this question is asking. I guess the normal force is going to be your weight plus ma, or ma plus your weight. I don't care. Well, this would be if there was no acceleration. But if we're accelerating, it's got to be more than, because we're adding to this, yes? So as long as A is greater than 0, normal force will be greater than your weight. It's got to be. You feel slightly heavier when an elevator starts to accelerate up. Or if we want to increase the acceleration, how many of you have ridden on the elevator before? Okay? When it accelerates you up, that acceleration is big enough that you really feel heavier. You feel like you're getting pressed into your seat. We said last year that your body is a backwards accelerometer. So if you feel like you're getting pressed into your seat, which way are you actually accelerating? Up, you're feeling heavier. Okay? Example 2 says, write a net force equation for the situation described in example 1. Done. I answered it on the fly. By the way, if we were accelerating down, which force would be winning? So would normal force be bigger, smaller, or the same size as your mg, as your weight, if you're accelerating down? You feel lighter. And that's the one that you've been on the elevator, right? It's much, I think, I've been on it a few times. It's more terrifying when it accelerates down. Going up, I'm okay with that because I've felt plenty of times heavier. But it's when I go down, that's when I reflexively grab the railing because I feel like I'm about to fly off my seat. I'm not. There's still a net force holding me on my seat, but I can't convince my brain of that. It grabs something. Am I? Yes? Are you feeling this? Yeah. I think most of you have been on an elevator. The bigger terror is down, I think, for me at least. So there's going to be an elevator question in your future. I like example 3. I like example 3. I like example 3. A student stands on a kilogram scale. So a kilogram scale reads normal force divided by 9.8. That's how they calibrate it. If the elevator accelerates down at 2.25 meters per second, find the normal force and find the scale reading. Okay? Diego, you know what this might be a good job for? A free body diagram. I'm going to do it on the left here so I have room to show work. Diego, what are the forces acting on this student? Get the obvious one.
Gravity.
Which way?
Down.
And now I'm going to put in mg because that's the equation for the force of gravity. What else? How do I know there has to be another force? If there was nothing else, what would the acceleration be exactly as a number? Not 2.25. Yes? So there must be a force pointing which way? Can you say that out loud so my YouTube up? Diego, let the record show Diego pointed at the ceiling. Which way are we accelerating, up or down? Read the question carefully.
Down.
So is the force up bigger, smaller, or the same size as mg? Yep, loud and proud.
Smaller.
I'll exaggerate it. What force is that? It's the scale pushing up through my feet. But what does the scale actually measure? Normal force. So, Diego, who's winning? Who's losing? Equals MA. I want to get the normal force by itself. What's right in front of the normal force that I don't like? Blech. This is where we called this the swappy dance last year. We said what you could do is you could plus the normal force to that side, and at the same time, you could minus the MA to that side. And you get this. mg minus ma equals the normal force. By the way, what if A is 0? Oh, then you get your normal, so that works with what I understand. If you're at a constant velocity, you don't feel any different. So I think I've got this equation set up right because it works for when a situation that I'm more familiar with. Let's crunch the numbers. So the normal force is going to be M, 35. G, Diego, do I put the negative 9.8 or just the plain old 9.8 in here? Because we took care of the negative with our winner, minus loser. That we took care of that, right? And then minus 35 times 2.25. In newtons, what's the normal force that this student is experiencing? I missed a times sign there. Y'all get 264.25? Okay. I'll just write to 3 sig figs 264, but I'll store it on my calculator. B says, find the scale reading. If I know a force in newtons, how can I figure out what the equivalent mass in kilograms lifting would be? How do I convert newtons into its equivalents in kilograms? I'll give you a hint. I think it mentions it in the brackets. Yeah, divide by 9.8. That's how kilograms on my scales are calibrated. It measures the force in newtons and just divides it by 9.8, and that's what that scale is calibrated for. So if I go 264.25 divided by 9.8, even though this student's actual mass is 35 kilograms, the scale would be displaying it as 27 kilograms. This student would feel 8 kilograms lighter. I should point out, not many elevators accelerate that fast. Some of the ones in like fancy hotels, like in Las Vegas, those ones do. You can really feel the acceleration through your feet, but like a standard 2 or 3 story apartment elevator, you can barely feel the acceleration. Even if you're looking for it, you can barely detect it. I like example 4. I like example 4. Example 4 is a nice question. Example 4 says, what is the normal force for the following object? Again, there is no formula on your formula sheet that says Fn equals something. You have to figure it out from a free body diagram. So this is a job for a free body diagram. Although, did they give me a picture? Okay, I'm going to label the picture, which technically isn't a free body diagram. Technically, a free body diagram is when you represent the mass Kelvin with a dot. But since they gave me a picture, I'm going to label my forces on here. What are the forces acting on this 5 kilogram mass? Get the obvious one. Yep. Is this mass sinking into the ground like quicksand? Is it flying into the air like Superman? That means that vertically the forces must be, I'm looking for a word that starts with letter B. Okay, now I'm going to give you the physics 12 version of that. That means the vertical net force must be 0. Balanced. Okay, so that means there must be a force pointing up. The force that's pointing up, is it going to be bigger, smaller, or the same size as mg? And convince me. Okay, the normal force is going to have to cancel out mg, which if I do the math, 49 newtons, and an extra 15 newtons. So the normal force, I'll exaggerate it, is going to be larger. I could do a full winner minus loser equation, but are we sinking into the ground like quicksand? Are we flying to like Superman? You know, if the net force is 0, what we're really saying is everything down has to equal everything down, mg and 15, has to equal everything up. There's the equation to calculate the normal force for this situation. But I'm not putting that on my formula sheet, because if you add extra forces, it's going to change. So it's going to be 5 times 9.8 plus 15. I can do that in my head. It's going to be 49 plus 15, 50, 64. Double check me. What if instead of pushing down with 15 newtons, what if we were lifting up with 15 newtons? Can anybody see in their head what my new equation would be? So instead of having that as a down arrow, what if it was an up arrow? What would the equation be? More specific, what would the equation be? What plus what equals what? It's still going to be everything up equals everything. So Fn plus 15 equals mg. And then to get the Fn by itself, you'd minus the 15 over. Which I think is kind of what you were saying. Okay. Example 5 says, given the net force acting on each object, fill in the missing forces on the free body diagram, and then circle yes or no if the object is accelerating. We're going to do the yes or no first. What's the net force on this first one? So is it accelerating, yes or no? Newton's first. What about this next one? Accelerating, yes or no? Must be. Accelerating, yes or no? Has to be. Accelerating, yes or no? Has to be. If the net force is not 0, it has to be accelerating. And I can even be more specific, in the same direction as the net force. Okay, now let's fill in the missing forces. I'm going to zoom in. How big must force A be exactly if the net force is 0? How big must force B be? Has to be. Ooh, the net force is 900 newtons up. How big must force C be? Good. Right? The net force is 60 newtons left. How big must force E be? Gotta be, because there's no unbalanced vertical force. How big must force D be? Don't forget units, Mr. Dewick. How big must force G be? How big must force F be compared to force H? That has to be H. That has to be F. And I think I told you last day, I'm going to start to do more algebraic with no numbers kind of questions with you this year. So let's look at air resistance. Air resistance is the force of air. Before you turn the page, there's one key thing you want to underline. Air resistance is the force of air molecules that bump into an object that's moving through the air. And the key thing, air resistance always has a direction opposite to the way that you're moving. So example 6, it says, draw force diagrams, free body diagrams, for each of the following. Situation A, it's a ball being thrown. Situation A is while it's in my hand on the way up before I let it go. Situation B is after I let it go while it's on the way up. Situation C is while it's on the way down before I catch it. So situation A is right here. Situation B was right there. Situation C is right there. Let's draw free body diagrams. Although, did they give me pictures? I'm going to label the pictures because it makes it a little clearer. So, situation A. What are the forces acting on it? Okay. What else? We could call it a normal force. You could call it F throw. I guess you can treat my hand as a surface and call it a normal force. I think what I'm going to do, Braden, is I'm going to call it F throw for this specific. And here's the big question. Is F throw bigger, smaller, or the same size as mg? And convince me. Can I show you a situation where it's smaller? Watch, 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 watch. Can I show you a situation where it's the same? Sorry for those of you on YouTube. Watch, 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 watch. Did the ball leave my hand? You know the only way the ball can leave my hand is if the upwards force is got to be larger. Otherwise, it's not going anywhere. Okay? If I had asked you this and you called it a normal force, I'd give you full credit. And we are, while it's in my hand, ignoring air resistance. But B, a rising ball, and they want me to include air resistance. Well, okay, first of all, what are the forces acting on it? Get the obvious one. What else? I guess air resistance. Which way? In the opposite direction of motion. You could put a little arrow like that. I find that confusing. If I have two forces in the same direction, I usually draw the other one just beside it like that, so I can clearly see that it got my attention that there are two forces. And I'm assuming that air resistance is less than gravity. I think it is. C. A falling ball, include air resistance. What are the forces acting on it? Get the obvious one. What else? Air resistance, which way? Bigger, smaller, or the same size as mg? The actual correct answer is, it depends. Because when I jumped out of an airplane, when I jumped out of an airplane, air resistance got bigger and bigger and bigger and bigger and bigger and bigger and bigger until eventually it matched gravity. We call that a special kind of velocity. You might recall the term. We'll include it in our notes in a second. But I don't think this is falling for that long. So I agree with you. I think in this situation, we can assume that air resistance is smaller. Yeah. Wait a minute. Situation B. What direction are the forces pointing? Both of them are pointing which way? Huh. How the heck is it possible in 6B for the ball to be going up if all the forces are pointing down? Have we screwed up? How can the ball be moving up when all the forces are down?
Ball slowing down.
Sorry?
Ball slowing down. The acceleration of the ball.
That last sentence you said made my little physics heart go pitter-pat. Can you say it again? You said it's not the something, but the something?
Not the velocity of the acceleration.
We have to be very careful. Newton's laws tell us nothing about velocities. They only tell us about accelerations, but it's very tempting and easy, especially if I throw a little mini curveball puzzle at you, to confuse velocity and acceleration. It's really, really tempting to do that. So Newton's laws tell us accel, not velocity. And let me see if I can move that up half a line. Let me do that. Well, right about there. So looking at that free body diagram, is it accelerating down? Well, yeah, it's moving up but slowing down. If you're moving up but slowing down, you must be accelerating down. So that works. Now, eventually, if you accelerate long enough, your velocity and your acceleration will match the same direction, but not always at the beginning. Example 8 says, write an equation for C. Oh, and I said it's speeding up. That's my way of saying you can assume that air resistance is not bigger than gravity. Who's winning in C? Who's losing? What's that always equal? Okay. Air resistance is a really tricky force because it's constantly changing. I mentioned that coming up. You've all probably put your hand out of the window of a moving car and you've done the little flying with your hand, but you may notice that when you change the cross-sectional area, the air resistance force on your hand changes. Also, the faster you go, the bigger air resistance is. You need calculus to really analyze that properly, and we don't have that skill. So we'll look at air resistance in little snapshots. Something like example 9. A 90-kilogram parachutist free falls for a time and then opens a parachute. If the parachutist slows down at a rate of 1.5 meters per second squared, A says compare the forces that act on the system. That's physics speak for you better draw a free body diagram. So I'm going to do part A right here. I could label the actual parachute, but I think it's going to be a little clearer if I don't. What are the forces acting on this parachutist? Get the obvious one. Good. What else? Air resistance, bigger, smaller, or the same size as mg? And how do I know? What? First of all, what direction are we traveling? Down. Are we slowing down or speeding up, according to this question? So if we're traveling down but slowing down, what direction are we accelerating? Which way must the bigger, larger, unbalanced force be pointing? So can air resistance be bigger than mg? We've just proved it can be. The fact that I'm alive proves it was. Otherwise, I wouldn't be here. Write a force equation. Okay. Austin, who's winning? Who's losing? Equals? If we were speeding up, it would be mg minus f air equals ma. But we're slowing down. That's what the parachute did. Austin, what C you want me to find? As far as I'm concerned, Austin, now that I've done this with you, I can either give you the acceleration and say find the force of air resistance, or I can give you the force of air resistance and say find the acceleration. How would you get the A by itself if I asked you that? Divide the M over. Divide everything by M, okay? For the rest of this year, as far as I'm concerned, if I show you the basic equation, anything from that equation is fair game, Justin, to expect you to get by itself. Okay? We've done enough formula manipulation that we're in the big leagues now. Anyways, I guess plus the mg over. mg plus ma or ma plus mg. So it's going to be 90 times 9.8 plus 90 times 1.5. I think I can do that in my head. Sure I can. It's going to be 90 times 11.3. It's going to be 90 times 11, 990 plus... Oh, hang on. Carry a 1, Mr. Dewick. 90 times 11.3. So it's going to be 990 plus 270. So it's going to be 990, 1,190, 1,200. Is it 1260? No, I'm off. I forgot. I carried a 1 wrong somewhere. I added an extra decimal. That was dumb of me. I can't do this one in my head, Mr. Dewick. 1,017. 990 plus 27, not 990 plus 270. Sheesh. Oh. I wrote here, so the force of air resistance is actually not a constant value. If you want to find out more about it, Google, do a YouTube search or a Google search for how to calculate air resistance. There is an air resistance equation. It depends on several things. It depends on something called the drag coefficient. That's the thickness of the liquid or the air that you're going through, because air gets thinner at different temperatures and altitudes. It depends on your cross-sectional area. And I think it depends on V squared. So if you're going twice as fast, air resistance is 4 times as big. If you're going 3 times as fast, air resistance is 9 times as big. And we'll talk about another squared situation in our future. Anyways, the force gets larger as speed increases. A falling object will eventually reach the point where air resistance equals mg, the weight, the force of gravity. When this happens, it reaches a steady speed that we call, does anybody know what we call this? Something velocity, starts with letter T. Terminal velocity. So if you look at the parachutist on the previous example, what would the force of air resistance be once terminal velocity was reached? Well, winner minus loser would be 0 because you're no longer accelerating. Or what would be a better way to write that equation? Not winner minus loser equals 0, but what would be a better way to write F air minus mg equals 0? Loud and proud, you're right. I would probably just say, look, they got to be equal, balanced. Oh, and now I can tell you exactly how big it is. How heavy was the 90 kilograms times 9.8? Well, 90 times 10 would be 900, so it's going to be 900 take away 18. Is it 882? Whew. Got back on the horse, Mr. Dewick. Threw me off once, but back on. Example 10, this is just as a thought experiment. I'm not going to ask you to sketch a graph on a test this year, but a parachutist jumps out of the plane and free falls. They reach terminal speed and they maintain that speed for a while. Then they open their parachute. They quickly reach a different terminal speed and then they descend to the ground. Sketch a velocity time graph. Do me a favor, can you cross out the word velocity and replace it with the word speed? Because you're going down, your velocity would be negative, and so our graph would look like this and everything would be below the x-axis, and I don't want that. So I'm just going to graph speed. So all of us right now do this, and on the y-axis put v speed. On the x-axis we're going to put time. This is just going to be a rough shape. I'm not going to put numbers. The scale is going to be wonky, but just to kind of wrap our brain around what's going on. So I'm about to jump out of an airplane. The airplane right now is traveling at a horizontal speed. I'm sitting with my legs dangling out of the airplane. What's my vertical speed right now? So there would be a stretch, I don't know how long that is, where my vertical speed is 0. Okay, I'm working up my nerve. I'm getting psyched. I'm ready to go. And now I jump. What happens to my vertical speed when I jump? Gets bigger, smaller, or stays the same? Bigger. Okay? Now, don't write this down just yet. Let's suppose that right there is terminal velocity. Here's my question. Does my speed increase do this, or that, or that? Is it linear, straight line? So, ready? Right when I jump out, what's my acceleration right away? Ignore the negative, but yet 9.8. But then as air resistance kicks it, 9.7, 9.6, 9.5, 9.1. So I think right when I jump out, my speed increase is at its maximum, but my speed increases slower and slower until that's when I hit terminal velocity. You don't need to put the X there. I'm just showing you. I think that's what it would look like. I speed up at my fastest initially, but I'm not speeding up as fast, and so it would kind of start to level off. Does that make sense? Who's my calculus students here? Okay, this is this is convex. And anyways, it's a decreasing derivative. If you're going to go all fancy schmancy. Now I'm at terminal velocity. This was when I was in free fall for a while. I was in free fall for about 30 seconds at terminal velocity. Then I pull my parachute. When I pull my parachute, what happens to my vertical speed? Okay, so don't write this down. Let's suppose that's my new vertical speed. Again, here's my question. Does it do that? Does it do that? Or does it do that? Right when I pull my parachute, I think that's when I'm slowing down the most because I'm going the fastest, and so air resistance is the biggest. So I think it's probably going to look something like this. Yeah? And then here's where my graph breaks down. Don't write that down. Don't write this next bit down. It took me probably 5 minutes to get to the ground. So I was at a constant parachute velocity for 5 minutes. If I tried to do that, this graph should extend off the page and way into Mr. Camosi's room if I was trying to go to scale. So we're just going to add a short, that's the parachute drifting to the ground. It should be way longer. Don't have time to fit that in. Then I reach the ground. What's my speed once I get to the ground? 0. And I think there, the acceleration is also boom, and then I kind of cushion my legs and land. I know I've done this graph right if from the side, it sort of looks like an old VW Beetle. It sort of looks like an old 1950s car, kind of. I'm not going to ask you to do that on a test, but I think it's a nice little thought puzzle, Alan. I like it. What's your homework? So you can try number 1, A and B. Number 2, so I told you more and more I would be just giving you purely algebraic questions. So number 2 says, write a force equation, not giving you numbers, at rest, accelerating up, constant speed, accelerating down. Just do the free body diagram, do the equation, then walk away. Because once you have the equation, Diego, I think I've taught you enough that you can find anything you need to if I give you enough data, right? 3 is good. 4 is good. 5 is good. 6 is good. Skip 7, skip 8. 9 is good. You can try 10. I stuck a little friction in there. 11 is good. 12 is good. 13 is good. We just had a Mars lander, but you can skip 14. But I wrote at the end of the lesson,